Have you ever looked at something so dark it looks like a hole cut out of reality? Not dark paint or a shadow, but a material that swallows almost all the light that hits it. When we look at everyday objects, we aren't actually seeing the objects themselves. We are seeing specific wavelengths of light that bounce off their surfaces and travel back into our eyes, sending a signal to our retinas. That returning optical signal gives everything shape and depth. Even the darkest standard black paints still bounce roughly 5 to 10% of the light that hits them back to your eyes. That provides enough of a signal for your brain to recognize contours, curves, and textures. Take a piece of heavily crinkled aluminum foil. Its chaotic geometry catches light from hundreds of different angles, creating bright highlights and deep shadows. But if you coat that exact same piece of foil in a material called Vantablack, those highlights vanish. The coating absorbs 99.965% of visible light. With almost zero optical signal returning to your brain, all perception of three-dimensional depth is instantly erased. Your brain is tricked into seeing a 2D hole in space. Beneath that illusion lies a precise physical structure, one that exists on a scale a billion times smaller than our own. Leaving the human scale behind, we plunge deep into the material surface, uncovering a microscopic landscape of incredibly tall, dense pillars. This landscape gives the material its name. Vantablack stands for vertically aligned nanotube arrays. It is a dense, microscopic forest of pure carbon tubes, packed impossibly close together. This diagram compares a normal flat surface to our nanotube forest. When a photon, a tiny packet of light, hits a normal surface, it bounces away. But when a photon hits Vantablack, it drops into the canopy of these towering columns. Once inside the array, the photon is trapped. It ricochets chaotically off the extremely tall, tightly packed carbon walls. Because the gaps are exceptionally narrow, the light cannot find the correct angle to escape back out. Energy cannot be destroyed, only converted. With every microscopic bounce against the carbon, the photon loses a little bit of its energy. Eventually, it is completely absorbed as microscopic heat. Vantablack doesn't block light. Its nanoscale architecture acts as a mechanical trap, actively capturing incoming photons and converting them entirely into thermal energy. To build a structure this precise, scientists don't use brushes. The material is carefully cultivated in sterile cleanrooms inside heavy, specialized reactors. The primary method used to make it is called chemical vapor deposition. The host object, like a piece of metal, is placed into a sealed, highly controlled vacuum-like environment. Engineers pump carbon-rich gases into the chamber and raise the internal temperature to between 400 and 750 degrees Celsius. These intense atmospheric conditions provide the exact fuel required for the carbon to grow. The carbon atoms separate from the hot gas. They seek out tiny particles of a metal catalyst placed on the surface, stacking themselves to sprout upward, growing perfectly straight vertical columns incredibly quickly. Achieving total darkness requires this intensive chemical farming process. It replaces the physical topography of the object, covering its natural surface with a light-devouring forest. If we leave the laboratory oven and travel into the vacuum of Earth orbit, we encounter a harsh lighting environment. In space, unfiltered sunlight creates an intense glare off any metallic surface. While artists and automakers have used Vantablack for visual stunts, often causing controversy over exclusive rights, the material was actually developed for strict industrial aerospace engineering. Out in orbit, aerospace engineers battle a constant problem called stray light. Ambient light reflecting off the Earth, the Moon, or even the spacecraft's own exterior hardware creates severe optical noise. This stray light blinds orbital telescopes. These multi-billion-dollar instruments rely on highly sensitive sensors designed to capture faint signals, and ambient glare easily overwhelms them. To capture sharp images of the faintest, most distant objects in the universe, engineers first had to figure out how to entirely eliminate the blinding glare of our own solar neighborhood. In a space telescope, intended target data, direct starlight, travels straight down the middle. Off-axis stray light hits the interior walls, causing reflections. But by coating those walls with Vantablack, the stray light is instantly absorbed, ensuring only the direct starlight cleanly reaches the sensor. Because the coating is so efficient at absorbing light, engineers don't need to design as many heavy, complicated mechanical shields. This allows the satellites to be significantly lighter, which saves millions of dollars on rocket launches. We see this exact application in star trackers, specialized navigation cameras that help satellites determine which way they are pointing. Stripping away the local light pollution allows these trackers to confidently lock on to faint constellations without any optical interference. By precisely arranging carbon atoms to trap and dissipate light, engineers have built a more effective way to see the stars. This engineered darkness lets us look past the glare of our own orbit to accurately chart the distant wonders of the universe.